Yes, I'm here to talk about delivering heterogeneous programming in C++, which, as I said, is a deliberately slightly provocative title because obviously C++ is a huge, important language used kind of worldwide, and to say that we're the ones delivering it is a little bit cheeky, but we are actually trying to make some strides in that area. So I was going to start with a little bit about me, but what I will do is I'll mention a little bit about Codeplay as well, since you asked. Codeplay, as I say, as Laura said, has been around for about 13 years in its current incarnation. And it was started by my boss, Andrew Richards, as kind of sort of games technology, is what he originally started out in. We developed a compiler called Vector C, which was for the PS2, and allowed, obviously this is like kind of way before I started working, but it allowed developers to target some of the PS2 was a little bit weird, or so I'm told, to develop for, and so it helped targeting that. Using, it allowed you to vectorize your code essentially at a point when that was a little less widely available than it is now. Later from that, we became an official tools provider for Sony, and helped develop some of the, I guess there was a game called NASCAR 2, which was running a bit too slowly on the PS3. And our technology had developed from there, and we were able to, do you know much about the cell processor that was in the PS3? And so it had these additional processors in it. Our technology allowed you to sort of fairly easily and without much change to the source code to target these additional processors, which were quite a strange architecture. There was like memory transfers could take varying times depending on where you were trying to transfer memory to and from. But with our tool, you could get about 90% of the performance for 10% of the effort. And so our code made it into this game. We're an official licensed tool provider. The ideas from that initial kind of effort in the PS3 is what informed essentially the majority of the stuff I'll be talking about tonight. That was like where it kind of came from. These days, we still have this focus on performance and providing that performance to as many developers as possible, but now with more of a focus on open standards and kind of portability and different bits of hardware, rather than just making PS3 games fast. So, that's kind of roughly, that brings us up to the current day. I'll talk a little bit about our future efforts at the end of this. About me, I graduated from Edinburgh University. It was about 3.5 years ago now, and I pretty much immediately started working in Codeplay. It was a postgraduate course I did, which got me interested in programming for GPUs. There was a program called LLR, which essentially you give it a very large number and it tells you if it's prime or not, which is, I guess it's kind of useful. It's quite, I mean, you've seen the great internet Mersenne prime search. It's related to that project, where essentially being able to do this primality testing as quickly as possible. And I found it very interesting, and it exposed me to the sheer performance gains you can get. Like, it was 50 times faster, I think, than my CPU, which is just crazy, just from changing to that kind of hardware. And so, yeah, that was what sparked my interest in this. Codeplay, very focused on this area, so I've worked there since I graduated. The projects I've worked on, I started out in research, but I also did some benchmarking, some debugger work, and kind of I've been all over essentially. That's like, I've been on quite a few projects in the company, and most recently I've been working in the C++ library for heterogeneous systems. So there's that word again. The contents of this talk will cover, first of all, what are heterogeneous systems? This is an important question to answer, obviously. How can we program these systems, and then what I think, or what the future looks like it's going to be, and how we might target them. I should also say that if anyone has any questions, please feel free to ask at any point. I'll be happy to answer them.
Perhaps you could start by those acronyms you got on the first line.
Yep, I will definitely cover them. So when I talk about a heterogeneous, or a device in a heterogeneous system, I would mean a device like a GPU, which is a graphics programming unit. So, the kind of traditionally used for accelerating graphics in games. DSP, which would be a digital signal processor. That would be something like a chip designed to transform the audio output from your phone into something you could send to a speaker, say, or for doing transforms on the audio data. Or even, I mean, it's just a digital signal, so it could be a video signal as well, for example. And the last one, FPGAs, are field programmable gate arrays, which is a terrible name, but that's essentially these devices which are, you can customize the the circuitry can be customized in the field. That's why it's field programmable, as it were, to customize for the task you're doing. Traditionally very difficult to program for, and that's changing now with the efforts of companies like Xilinx and Altera. They're doing some really good work in that area. Generally, like that, those are the specifics, but generally what I mean is there's some bit of hardware which is more specialized than and is fundamentally actually different to a CPU, central programming. The specialization can make it very fast. As I said in my dissertation, I saw 50 times speedups or more. But it's also harder to program because of these specializations. Their fundament is not the same as writing essentially linear bit of code that will run on your CPU. So what is a heterogeneous system? If we have these devices or in a system, what's the full system? A heterogeneous system, I would say, is composed of a host CPU, which is a traditional CPU that we all know very well, one or more of these heterogeneous devices, and consists of some way to transfer data between the devices and the host CPU. It might be shared memory, it might in a mobile phone, or it might be across some high-speed bus like PCI Express, which is the one that you traditionally find in like a desktop system for communicating with the graphics card. And mobile phones, like modern mobile phones, are a really good example of this, because they have, I don't know the specifics, but this one will have, some bit in it for audio output, because they all do now. And more mobile phone companies like Qualcomm, for example, are devoting space on the actual die to graphics card hardware, or no, graphics card, I should say, graphics hardware, which is quite a difference compared to, say, a few years ago, where it was very, very simple systems. They're now hugely complex bits of silicon with lots of different devices dotted around that all do different things. I will provide, this sounds really dry and technical, but I'm afraid it'll probably help. I'm going to provide some definitions, just so that when you see a thing, or when I'm talking about a thing, hopefully make more sense. When I talk about the host, I would mean the CPU or code that runs in the CPU, that controls that controls the main memory. It's going to have the thing that has a memory management unit on it. Might control many of these devices attached. So that's like the traditional bit that we all know. A device, in contrast, would be a GPU or a DSP, something more exotic, depending on exactly what hardware you have. But conceptually, this is a split. We've got the host and the device. That's the big difference here. A heterogeneous system is therefore a host, a device, and some sort of API that allows you to target the devices. A kernel. So this is, if you have some computation that you would like to target one of these devices with, the kernel is the code that represents that computation. It is a special bit of code that you can then dispatch onto the device and then get a result back later on in time. Going into slightly more specialized definitions, a work group is a collection of work items executing on a device which are executing that kernel that you have defined. And that, I promise that will make more sense later on when we get some other stuff. They will probably have some kind of shared memory between these work items. And this is where one of the main differences comes. They all are executing the same instructions. So obviously, in a multi-core, because you might well say to me, well, you have multi-core CPUs now. You're not looking at one thread, you're looking at 4 or 8, or servers will go higher than that, right? So what's the difference? Well, in a GPU, they all have to execute the same instruction within this work group. And we've got a little diagram later on that will kind of explain why that is the case. A work item is a single thread or task on a device that will be executing in parallel with lots of other work items at the same time. So that's work items are a group of work items in a work group, and the total number of work groups is like your full computation, as it were. This is the last one, I think, I promise. Yep, last one. A parallel for is a very common concept in computing, heterogeneous computing, is a number of work items composed into work groups, executing a kernel in parallel. So that's why I've got these definitions before. You're talking about the kernel being executed on multiple threads at one time and then providing some sort of result. Generally, it's not like calling a function. It's probably going to happen asynchronously, and you're going to have to transfer the results back from the device. So it's more like you say, go off and do this work, and then, I don't know, maybe give me an event that I can query to find out when the work has been completed. So that's our definitions. I promise that's the last of like the technical kind of stuff, or like the technical direction, kind of boring. An example heterogeneous device. So CPUs today, they're hugely complicated, like some of the most complicated bits of technology on the planet. I think are it's actually incredible to me, obviously. But you can execute instructions out of order, or speculative execution based on branch prediction, prefetching instructions and data from memory. There's obviously a huge amount of stuff that goes on, even in what might appear to be a simple code. There's generally a huge amount of stuff going on in the background the programmer doesn't really see. That complexity is all hidden from you, essentially. In contrast, for example, we'll look at a GPU here. Most GPUs will have lots of execution units, so the things that will actually perform the work of each individual instruction. And conceptually, there could be hundreds, or even you'll have seen some of NVIDIA's latest cards, thousands of these things on a single graphics card. But they have far fewer scheduling units. All the cores have to execute the same instructions on different data, because the CPU has like multiple instruction decoders going on in parallel to work out what the next 10, 20, more than that instructions will be, and speculatively decode them. Here, you've got one, maybe one per 32 execution units. So they all have to do the same thing because there is only one scheduler for each of these, say 32 of these. And this is a diagram I alluded to earlier. It will look kind of something a bit like this, more complicated obviously. This is quite similar to a diagram that NVIDIA provided if you were looking for more information. Here we have a processing element, which is like a single kind of core that can do a thing, an add, a multiply. It'll have some private memory, which is basically a set of registers, much like the CPU. But you can see here that there's just the one scheduler. And this scheduler is the one that's telling each of these cores what instruction to execute next. So they all have to be doing the same thing. However, they have their own copies of memory, so they can be executing on different bits of data. So if you have something like a for loop, which is, say, given as C++, say something like a transform, where you're taking an input, doing the same operation to each element, and then outputting. That's the kind of task that works very well, because here we can map each element of that big array, say, to each of these cores, and it doesn't matter that everyone's doing the same thing, because that's what your loop was designed to do. Here there's, this maybe would be some local shared memory, so that they could do some local communication based on that. And this register file is an important detail, which I will maybe cover later on, but allows you essentially to deal with some of the other complexities of working with that.
So the processors aren't working in lockstep, they're working autonomously.
No, they are in lockstep.
They are
exactly in lockstep. Yep, for sure. And that's one of the kind of complexities that you have to deal with. If you can imagine having if statements in any language you're executing this, it just suddenly goes horrible, right? Because how do you deal with an if based on data, right? So that's a good question. Yes, so this example continued. As I mentioned, you'll have typically about 32 processing elements in a block. A block is what NVIDIA term, but you can imagine that mapping to a work group, essentially. There will be lots of these blocks per GPU. There is also global memory, so when you see like the technical specifications of, for example, a GPU, and it tells you the new AMD thing has 2 gigabytes, 4 gigabytes of RAM, that's what they mean, this global shared memory across all blocks. But it's really, really slow. It's very high bandwidth, but the latency is huge. That's what that register file is for. Essentially, it allows you to swap out all computation while waiting on main memory accesses. So this is another kind of strange feature or, I guess, quirk of GPUs. This memory is not generally shared with the host either, so that's why you have to schedule these memory transfers. You have to say, I'm going to need this data, push it onto the PCI bus, for example. In In the PS4 is a counterexample to that, in that the memory is actually fully shared across the host and the device. Similarly, most mobile phones, it's shared across the host and the device, but that might have other downsides. It's a design decision, it's fair enough. That's how, by exploring this kind of design space is how we're going to get interesting devices out of it. Yes, and here I'm saying it's fastest to swap out thread. If a thread does a global memory read, it's fastest actually just to swap it out and wait for that read to be, or stored even, to be issued, to be completed, and then do work on other cores. Sorry, on other threads, I should say. This architecture that I've kind of described is GPU-like. That's roughly what it looks like. The ideas apply across different bits of hardware. There might be slight details that are different, but like this general concept of many threads, shared memory, but less schedulers is like the kind of general idea. A DSP has similar concepts like a reduced instruction set. You're not going to have as general instructions that you can actually dispatch. Maybe the DSP has no virtual memory support, so that you're back to, I guess, kind of quite older thing of not having unlimited virtual memory. So the question is, how do I program something like that? If it's so different to a CPU, to a host, how do I actually target these data things? How you program something like that? There are a lot of APIs available for doing this. And there's 4 that I'm going to talk about tonight. There's more than that, but these are kind of like, I would say, 4 main approaches, I suppose. You might have heard of OpenMP or OpenACC, which is commonly used in high-performance computing. CUDA is obviously huge. It's everywhere. That's NVIDIA's API for targeting GPUs, for targeting specifically their GPUs. It's very successful. It does have this issue that you're then locked in. Like if you write all your code targeting CUDA, you're running on NVIDIA forever, right? OpenCL is an open standard. So you've probably heard of OpenGL. OpenCL, if you're not aware of it, is developed by the same group, the Kronos group, which is a consortium of lots of different companies. We're involved in it. And it's very similar in a lot of ways to CUDA. Originally developed by Apple, actually, funnily enough, and allows you to target kind of these heterogeneous devices. And lots of companies have provided an OpenCL implementation for their hardware. And the last one I'm going to mention is the one that's closest to my heart. It's called SYCL, and that's one that we have been very heavily, it's another open standard, we've been very heavily involved in standardizing that, and actually have been working on implementing it. That was what I was working on like last year. These are independent standards that work with languages, like there are libraries, you can provide them as libraries. Most of them will have some kind of C interface, for example, or maybe like a few of them will require specific compiler support. So they work with the language, but are not a core part of the language. I'll briefly cover some of these APIs, maybe not. OpenMP or ACC, these are directive-based APIs. So you take standard C code, and you do something like hash pragma parallel for. And I mean, OpenMP has been around for years at this point, and it's pretty good for what it does. Again, you can have a for loop where you can just put your pragma on top of it and it will dispatch it to multiple threads. Or on a high-performance computer like Archer down near Edinburgh, you could have it dispatch across to multiple nodes of a computer. It is very, very easy to get started. It will go back to linear execution if it's not supported, which is also nice because it means you've not broken anything, right? And it may even require no changes just to start. However, it is limited. If you want to support, they call them accelerators, so this is my notion of a device. You need to go to like OpenMP4, which is quite new still, if you want to have any kind of accelerator support. OpenACC is similar, but again, was originally targeting NVIDIA, so our friends NVIDIA doing their own special thing. It sounds like I'm really ragging on them, I'm not, and it's fair enough, they wanted the support, they developed it. Recently, OpenACC and OpenMP kind of resolved. I want to say there are differences, but the standards have now kind of converged. So it's a very quick way to kind of get started, and that can be really powerful for just kind of prototyping type thing. Code sample, be very quickly, look at it. Essentially, you're saying target a device. I'm doing a parallel for, and this example here would do something like calculating sine of a whole bunch of numbers across n. N could be like really big, and it'll batch it all up and dispatch it for you to a graphics card. You would need to do other stuff to be able to get the memory on and off, but for this sample it's kind of showing how close it is to like plain C, just with these directives. So yeah, super simple to get started. You can do more complicated things. You can determine your own scheduling, for example, if you want to choose what size the blocks should be and so on. But it is quite limited. You're only actually targeting the code that's in a private block. You have to put that there. And it is lacking in fine-grained control. So you'll get like a lot of the performance, but you might not get all of the performance just by starting with this. CUDA is a different standard. As I say, this is NVIDIA's standard. It runs on NVIDIA GPUs only, though I suppose I should update that as AMD has been making some interesting they've been attempting to run CUDA code on their own hardware. It's an interesting area, but I've not looked a huge amount into it yet. It's quite a new technology that they've got. Performance can be amazing in this. As I say, I coded in CUDA for my dissertation, and it just, it blew the whole CPU away. It was incredible. However, you are then tied to one platform, CUDA, NVIDIA. It gives you a lot of control. You can control where the data lives, when it's when transfers actually occur, and to what extent or to what kind of breakdown of blocks and threads you actually want to execute for. The code's written all in one single source file, and you have explicit kind of device like annotations. So here, this global void square element, this squares every element of a complex number, essentially, of an array. And this global is necessary to say this is a device function, and they have a special compiler which will go in and do some magic, effectively, and you end up with a device function that will execute in the GPU. The actual dispatch is done to the GPU through code like this, and you can then do things like get the last error to see if you actually executed successfully, device synchronized to wait for the execution to finish, essentially. CUDA is available from NVIDIA. You can go and download it, and it's sort of relatively easy to integrate. It behaves like ordinary C and C++, but you do need this additional compile step to be able to get the device code emitted. You can progressively parallelize by moving more and more of it to CUDA. You can start off by doing like a very simple bit, and then add more and more over time. So there are advantages there for sure. OpenCL is very similar to CUDA. But this one is the one that is developed by Kronos Group and is freely implementable. Anyone can actually implement it. It's much more varied in terms of what you can target as well. Lots of these devices that I mentioned before. The host API is plain C, so that's very portable as well. And the device side code is also actually very similar to plain C. There are some restrictions. Which relate to this hardware, essentially being no function pointers and no recursion. You can. Working out how to do that on the device would be very, very technically challenging, I guess you would say. Hardware is just not capable. The interesting part of this, so I guess a few of you guys said that you'd done kind of Java work. So in Java, you compile to like an intermediate bytecode, which then is like compiled at runtime by the jitter that you've got, the JVM. That's actually a very, very powerful idea. And recent versions of the OpenCL standard take that idea as well. You compile your device code offline into this intermediate language, and then you pass it. So that means that you can spend more time like doing optimizations on it and doing some important transforms, which you then, when it comes to runtime, that means you have to spend less time before you can actually execute your code. So that's a very powerful technique, and it's really only, I guess, in like the last 3-4 years that that's become available. And that's something that we've taken advantage of, which we'll get to on the next couple of slides. So the kernel code, it looks very, very plain C, but you still have to say things like kernel, this is a device kernel. Global, this lives in the global memory of the device. It provides some functions, free functions to tell you, like, I'm at this index of my array. There are lots of math functions as well if you need to do mathematical operations. It's quite interesting. It's a good technology. there are still other APIs from other vendors that all do different things and solve different problems. There's HSA, C++ AMP, RouterScript from Google. Obviously Vulkan is very new, again another one from the Kronos group. Direct Compute from Microsoft, that's their compute part of their DirectX API. They're all relevant, and they're definitely worth looking into if you want to. I just don't really have time to cover them. And we see that these APIs are often different, but some places they kind of overlap in their ideas. Good in OpenCL, the kernel code is separate and has to be marked out as being device code. Or maybe they have separate memory between host and device. Maybe they tend to work best when you have big broad arrays where you're doing the same operation on every single element in this kind of big lockstep. And we also see that often they're fundamentally asynchronous. You can queue work and then later on wait and say, can you give me the answer now, and then transfer the memory back. So the standard I'll now cover, and I guess this is the one that, as I say, we like the best, is the one we've worked the most on, is SYCL. It is still from Kronos. It is similar in some respects to CUDA, but it has different features compared to these other ones that we saw previously. I mentioned this intermediate language, so Java compiles down into JVM bytecode. If we can compile our OpenCL C kernels down into bytecode, why can't we just compile anything down to that bytecode, right? The implementation isn't going to know what we started out with, so why not C++? We can use C++ function objects to identify what a kernel is in our C++ code, or even a C++ 11 lambda, which is quite a nice feature. You can use those to say, this is actually my kernel. However, it's still also ordinary valid host code, and you can execute it as such if you need to instead. It will be slow, right, because you're not running on a specialized device. But conceptually, it's now the same code running on host and device. We still inherit, it's built upon OpenCL, and therefore we inherit restrictions from it. No recursions, no function pointers, and your kernel has to be void. It's operating on some global memory and then maybe getting transferred back across. It does use the OpenCL API underneath to talk to the devices and to do all the work, but it sits on top of it as a layer. SYCL as an API, there are classes for each of the OpenCL types that are kind of exposed, like a device or buffers for CL memory objects. The data is controlled by these buffers and accessors. A buffer is what you wrap it in to kind of notify the SYCL implementation, this is data I want to work on. Accessors tell it where you want to use it. So in contrast, OpenCL you have to say like, do a memory transfer, do the computation, transfer it back. In SYCL, the programmer describes, I want to use this data, and then it orchestrates the data movements for you by making sure that it's kind of available. It's not just convenient, because obviously you then don't have to say I want a copy of memory, but it also means that the runtime can schedule it efficiently when nothing else is happening. Or if you're not actually using any data, it won't move at all. I've got a brief sample here. So like this is a kind of an example of SYCL code, and this kind of works and runs today. In terms of, so first of all, we've got some STD classes here, which are nice. And then all the SYCL code is like, what's now the equivalent OpenCL for this is literally like over 200 lines. So that's why we're really proud of the fact that it's so much simpler to kind of get stuff done. And this is a super simple example which does, it adds two arrays together and stores it in a third one. Groundbreaking, I understand. But essentially, this is like the absolute basic stuff that you need to get started. We have a queue, which is like a sort of a conceptually where you queue up your work that you want to be executed in some device. Ranges are how you define the size of work that you want to do. In this case, it corresponds to the size of all the arrays. You can see that's that parameter n there. We wrap all the data in buffers, accessing a data member, which is saying we're going to be using this for computation, and then we submit. The work we submit, first of all, we say these are accessors. Access, essentially notifying the system that you want to use these, and unfortunately, the font's pretty terrible color there. The first two are saying read, so you're saying I'm reading from these two. Last one says write, because that's the one that we're outputting the data to. After that, it's just this parallel for, saying we're doing a parallel for each element, add two of them together, store the third one to it. And so that's a lot simpler to actually get started in and start doing parallel stuff in the GPU than a lot of other of these APIs. It looks a lot like C++. It is very much ordinary C++. There's no separate kernel string, no device annotations, no pragmas. And why am I showing you this? Well, obviously we are kind of invested in it, but it is an independent open standard written by the Kronos group. But what about standard C++, ISO C++? And actually there's a lot happening this week if you guys follow at all. You know, obviously we're working on the standard, the meetings this week for C++ 17. Yes, so in C++ 17, one of the technical reports, like a new proposal for the language, was the parallel STL, which takes all the STL algorithms like transform or sort or reduce and allows you to suggest that you want it to be executed in parallel, be it through multiple threads or perhaps on one of these devices that we've seen. And it's as simple as adding an execution policy to any of the function calls, which the execution policy says execute this in parallel on a device, on the DSP, whatever. The policy is what allows library writers, people who want to implement parallel STL, to control how it should be parallelized, be it, as I say, through threads, or actually, that's a good point, you could even do this for like a distributed machine, like Archer or something like that, or like a supercomputer, or dispatched on OpenCL sequence, which is what we did. So the parallel STL, the fact that it made it into C++ 17, it is clear that there is an appetite for improving the standard C++'s support for parallelism, because it's kind of not really there right now. And there is work happening in this area. One interesting one is, like, say, a future where you bundle up this asynchronous work inside the future, which it then goes off and it will work on it for some length of time. And then you ask for the work to come back. You have it's a promise that is then fulfilled. These are useful for hiding the fact that it's asynchronous, because you kind of wrap it in this future and then get it later. And it provides this clean demarcation of, like, this is where my parallel code is. It's all inside this future. And there are lots of ideas at the moment for how to bring more parallelism into the standard, but no actual decisions have been made. They want to make the best decision ever. I'm sure you've seen some of the mistakes like the committee has made over the years. Export for one, one compiler team managed to implement export. They don't want that to happen again. I would say that I don't think any one API that I've kind of described here so far is like the true answer, not even SYCL. But I think we can learn lessons from each. This has been going for quite a few years now. There's clearly a lot that we can learn from in terms of getting the best possible solution into the language. Ultimately, it's going to require input from the community. Any person can write a proposal and have that put into C++. So what about the state of things today? OpenMP is implemented in lots of compilers. GCC supports it, for example. OpenCL, you can get that from vendors like Intel, AMD, NVIDIA have their own OpenCL implementation. You can get CUDA from NVIDIA's website. Compute CPP. This is the this is the implementation of SYCL that we have been working on. And when I first gave this talk, I had to say soon. And fortunately, I can actually say today. You can go download it, give it a try, play around with it if you like. And if you've got any bugs and you send a bug report, I'm actually the person that will answer it as well, so please don't. Heterogeneous computing, the whole point of this talk, it's only going to become more prevalent. So it's never really too late to start. It's a trend that we've seen. If you look at Intel's CPUs, if you look at AMD had some interesting technologies in that area. More and more of the actual transistors are being devoted to parallel GPU hardware, because we're kind of hitting a wall with like the speeds of CPUs. There's not a lot else that we can do there. But GPUs, they're really becoming the next new thing. What about tomorrow, the future? C++ 17 is a smaller release than was anticipated. The committee doesn't want to introduce stuff that's half-baked. They want stuff that's been tested. Stuff like, I don't know if you noticed or had investigated much, but concepts didn't make it in. Modules didn't make it in. Those were two really hugely, like the community was crying out for them, but no one had really worked with them, and they didn't know if they brought it in or were we making a mistake. So it's better to have something which is, well, non-standard, but a proof of concept out there early that people can use, can try, can break, fair enough, but we can get these kind of lessons learned from this. Other bodies aren't stopping. Kronos is developing and improving its standards all the time. Work has started on the next version of SYCL, 2.2. OpenCL is out at 2.2. They are already working on new versions of the Vulkan standard. Like, it's always moving forward. Here I have some useful links, and I'll make sure the slides are available if you want to have a look at them. And yeah, that's everything I have to say about it.